All right, let's start. So I uploaded 2 slides to the Canvas. I'm not going to cover the second one, but you are encouraged to, go through the second slides as well, because it contains some extra content. Okay, so this lecture is the last one for this semester. Actually, we already studied a little bit about kernel methods, right? Kernel, nonlinear, SVM, kernel PCA, kernel LDA. So today's lecture is really just show you how we can kernelize a linear method in machine learning. Actually, there are quite a few linear methods in machine learning can be extended to a nonlinear case using this so-called kernel trick. Okay, it's also basically the procedure of kernelizing a linear method. All right, so I guess most of you should already because we learned this classifier like a linear SVM, and a linear regression, for example. We say that in the real world applications, in most of the cases, the underlying distribution cannot be well represented using a linear representation, right? So in nature, it's nonlinear. So in many cases, we need a nonlinear classifier or nonlinear regression. So here I just show you an example. This is of course a linear classifier, but it may be for more complicated cases. For example, if we have such a data set, it's not possible to find a linear classifier to get very good accuracy, right? In this case, we have to using a nonlinear classifier. All right, so in the case of nonlinear SVM, we say that in the original low-dimensional space, it's very difficult to well separate the data points. So then what we can do is we project the original data into a higher dimensional space. In the higher dimensional space, the intuitive idea is in a much higher dimension space, the original data points will become very sparse. That's easy to understand, right? Because now it's very sparse, it's much easier to find a linear separation, boundary in the high dimensional space. Actually, if you use a RBF Gaussian kernel, the underlying dimension is infinite. Okay. So we have an example here. Actually, I believe we showed this example when we studied the spot vector machine. So the original data is in 2D, right? So something like this, and you will not be able to find a linear Gaussian boundary. Then we can just use a very simple transform, okay, to lift the 2D data into 3D with such a projection function, and then this is the data lifted to the 3D space, and in this space we can find such a linear hyperplane to separate the 2 categories of data points, right? That's the high-level idea. And the good thing about the kernel trick is we do not need to know this projection function explicitly. Right? We only need to know how we can calculate the inner product in the transformed, in the projected space. And we use this kernel function to calculate this inner product. So we do not need to explicitly define this projection function. Here we have a demo.
It all starts when you just add marvelous.
Anyway, see So the original data in 2D is not linearly separable, and then we can project the 2D data into 3D. Right? So this is the you lifted the data into 3D, right? So this is 3D. This is the original 2D data, and then in the 3D space, we just find this hyperplane to separate the two sets of data points. And if we project it back into 2D, then if we project this 3D hyperplane into the original 2D, it corresponds to like a circle, right? It's nonlinear. So that's the idea. So, the projected space, its dimension is almost always higher than the original one. As I said, because we want to make the data sparse in the projected space. And of course, the transform function can be any function, right? But as I said, it's not explicitly defined. It's implicitly defined through this kernel function. All right, and this can be related to the idea of extracting features. Here, I just show you an example of, given a RGB image, right? We do not use the raw pixel value as the representation of the image because it's not powerful enough. So previously, what people do is we can use this so-called histograms of oriented gradient. Right? So the idea is that you calculate the gradient for each pixel, and then you bin each the gradient of the of each pixel into a histogram according to the angle of the gradient, the angle or the orientation of the gradient. And then use that as a feature to do, for example, image classification. In this case, to detect the pedestrians. So this is transform, right? You transform the raw RGB pixel value into another representation, which is the histogram of oriented gradient, so-called Hogg features, right? So in this case, we know we actually heuristically manually design this feature transform function. Okay, so that works, right, for some of the problems. For example, the the example I just showed you. After you extract the Hog features, what people do is usually you can just train a linear SVM to do the binary classification. So this, the dimensionality of the projected feature, the mapped feature, can be very high. In the Hog feature, it's not that high. Usually it's less than 100. In the Swift features, it's 128 in most of the cases, right? But it really it's heuristic. It depends on how you design the features, but it can be very high or even infinite, right? And the computation cost can be heavy. The most important thing is it's not that easy to explicitly design this transform function, right? It's all heuristic. It's just, people use some domain knowledge to trial and error and find, okay, this works. But usually there's no, theoretical analysis why it works. Right? So the kernel trick is to define this transform function implicitly, okay, using this kernel function. And for many of the algorithms, including support vector machine and quite a few dimensionality reduction or feature extraction algorithms, we are only interested in the inner product of the mapped features. Okay, let's say this phi is the transform function, and phi x transform are the projected transformed features of the original data, which is x here. And in most of the cases, we're only interested in this inner product, right? Just recall the do formulation of support vector machine, right? It's wholly defined. The object function is wholly defined by the inner product of these features, right? So this is the key of this the idea of how you can kernelize a linear machine learning method to make it to generalize it into a nonlinear case, right? So what do is you just replace the original feature with this transformed function, right? And you don't need to know the transform function explicitly, right? You only need to know this inner product, which is defined by the kernel function. Okay, so that's the whole idea. And this kernel function can be more compact than the feature map, right? I believe that's easy to understand. This feature map, the dimension of the feature map can be very high. Let's say if the dimension of the feature map is a few thousand, right? And the size of this kernel matrix is independent of the dimension of the feature map, right? The size of the kernel matrix is defined by the number of the data points, right? So if you have, say, 1,000 data points, then this size of the kernel matrix is 1,000 by 1,000. It's nothing to do with the dimension of the feature map. Okay, so then as I said, if we do not need to explicitly define the feature function or the transform function, we only need to know how to calculate the inner product of the transformed feature map. which is the kernel function, right? So then we do need to define the kernel function before we can solve the problem, right? There are quite a few kernel functions you can use. The most popular ones might be one is polynomial kernel, the other one is RBF Gaussian kernel, right? So this is the polynomial kernel, right? And in this polynomial kernel, we have two hyperparameters. One is the offset C, one is this order D, right? And once we just set C and D, then this kernel function, can be expanded, right? Here, just show you an example. When D equals 2, that's quadratic, right? That's a quadratic kernel. Then pretty much this is just you expand it. That's the example we just showed you. You can, basically project the if the original data is in 2D, then you project it into a 3D, right? So that's the polynomial kernel. And okay, so this is in the case of D equals 2. This is equivalent. You actually explicitly transform the original data into a high dimension, right? All right, so here we have a question, right? You can calculate the inner product by using the kernel function or using the feature transform, right? Which one is more efficient? You can just do a simple calculation. Actually, there's a. Or maybe I will ask you the question later. So the second popular kernel function is the RBF kernel. Actually, in at least for like support vector machine or PCA, LDA, this RBF Gaussian kernel is more widely used than the polynomial kernel, right? And in most of the cases, this Gaussian kernel is the default one. Right. As long as you choose this sigma, which is the bandwidth or the variance of the Gaussian kernel, properly, it works very well. Okay, it works, at least as well as other kernels. So, if you don't know which kernel to use, just use RBF kernel. But you do need to set this sigma properly using, for example, cross-validation. And in the case of Gaussian kernel, actually it corresponds to you project the original data into infinite dimension space. Why is that? Because if you use this Taylor expansion to expand this RBF Gaussian function, it will have infinitely many terms, okay, which correspond to, infinite dimension space. So really, at a high level, when you use kernel function to compute the distance or the similarity between data points, instead of just calculate the inner product of the original data, when you calculate the inner product of the original data, let's assume the original data is L2 normalized, which means the L2 norm of the original data equals 1. Then the inner product measures the similarity of a pair of data points using the cosine distance. Right? It's the same as the cosine distance. It's the angle of the two vectors, x and x prime, right? So this is a cosine distance. But if we use the kernel function, it's just you know, you instead of using cosine distance, you use another measure of distance or similarity. Okay, so that means most of the similarity metric can be used as a kernel, but not all. Okay, why is that? Because some of the similarity distance will lead to a non-positive semi-definite kernel matrix, which will make the optimization very difficult. It does not mean you cannot use it, but it just means if you use such kind of kernel function, you know, the optimization will be non-convex. Okay, the objective function will be non-convex. There's a kernel function called I think it's tangent kernel function, which will give you a non-semi-definite kernel matrix. Okay, so one of the criteria for a valid kernel is that this kernel matrix must be able to decompose into a unit product, right? Actually, this is equivalent saying that this matrix K must be positive semi-definite. Okay, so a matrix transpose and times itself. This makes this, you know, the inner product of the, you know, the resulting kernel matrix must be positive semi-definite. Okay, I believe I mentioned this concept of semi-definite matrix in the first week, right? It means that all the eigenvalues of the matrix must be non-negative, okay? And it also means if you given an arbitrary vector A, this A transform times K times A must be a positive or non-negative value. Okay, and there's this. If we extended it to like a continuous case, then this is equivalent to this so-called Mercer condition. All right, so actually we already covered this a few weeks ago, right? So this is the primal formulation of the linear SVM. The first term here is the regularization. Second term corresponding to the hinge loss, okay? And this is soft margin linear SVM. In this primal form, if we want to solve this primal form, we have to somehow access, you know, this original data, the feature xi, right? The xi is the original data. So it will be very difficult to apply this kernel trick. So if we really want to extend this primal form of linear SVM into nonlinear case, what we need to do is we replace this xi, each data point, in by the transformed features, right? So it will be like a yi w transpose phi xi. Phi xi is the you know, the feature map, the projected features of the original data. Then in this case, we need to explicitly know how we calculate the feature map So instead, we find the due form of the original primal SVM. So this is the due form, okay? And these two are the KKT conditions. So alpha is a due variable. So let's check this objective function. We can see that the original data, xi, xj, only appear as a unit product, right? So this is a unit product of the original data. It's the same as xi transpose xj, right? So now, what we need to do is to get a nonlinear SVM. We replace xi, xj by phi xi, phi xj, right? And then we need to calculate the unit product of the Fitch map, the transformed Fitch map. That's the kernel function, right? So this will be the okay. Just compare the linear case with the nonlinear case, right? We'll replace xi by its Fitch map. So we only need to know how we can calculate the inner product of the transformed features. That's the, we calculate it using a kernel function. So here we're just, define a kernel function, k, xi, xj, okay? And this kernel function can be, polynomial kernel or IBF Gaussian kernel. All right, then we can solve this problem, right? Same as in the case of linear SVM. And likewise, the decision function for the kernel nonlinear SVM, all you need to do is just replace the original xi, the feature, by its the feature map, the transformed features, right? And then we just we calculate the inner product with a kernel function. That's all we need to do. Okay, just here I show you an example of the kernel nonlinear SVM. So this is the decision boundary of learned by the nonlinear kernel SVM. As you can see, of course, in this case, the decision boundary is nonlinear. It's not a straight line, right? For linear SVM, it will be a straight line. So, of course, the nonlinear kernel support vector machine produce more flexible decision boundary and can lead to better classification performance. That's expected, right? So I guess, we can view the linear SVM as a special case of the nonlinear SVM. In that sense, the nonlinear kernel SVM is more general than the linear SVM, right? If the kernel function is linear, right, which is, k xi xj equals xi transpose xj, right? The kernel function just calculates the inner product of the original data. Then this is just the linear SVM, right? And choosing a good kernel is a key to success. Okay, so as I said, the design of kernel function is actually, still heuristic, right? There's no theoretical guideline, what kind of kernel function you should use. And for most of the kernel function, there will be one or two hyperparameters. And those hyperparameters have a big impact on the final accuracy. So the rule of thumb is, if you don't know which kernel works best, just use RBF Gaussian kernel. But in the case of RBF Gaussian kernel, you do need to pay attention to the hyperparameter sigma, which is the bandwidth of the RBF kernel. Right? Typically, you can just use cross-validation to select the, the good one. So if you use a linear kernel, then this is just linear SVM, and you can use polynomial kernel and RBF kernel, right? In computer vision, especially for like image classification, object recognition problems, people also use this, histogram-like features. Okay, here I just show you an example. This is actually for document classification. Just assume you have a document which contains, of course, a lot of words, right? And you want to classify this kind of documents. How do you find a good representation to train a classifier? So what we can do is using this histogram-like features. So the idea is very simple, right? You have a vocabulary because the vocabulary will be limited, and for each word in the vocabulary, you just count the frequency, right? And then use the frequency as numerical features to represent this document, right? And this can be extended to images as well. So this is called bag of words features. I'm not going to talk about the details, but in the case of images, the words will be a vector. It's continuous, right? So you need to actually we use the k-means clustering to find a dictionary for the vectors, and then use the same idea to calculate the histogram to represent each image. After you calculate the features, then you can either use linear kernel or RBF kernel. Sorry. So this after you calculate the histogram features, you can train a classifier. In this case, you can use a lot of similarity measures to be the kernels. Actually, you can still use linear kernel or RBF kernel, but they may not work best. Okay, so because the histogram is a discrete version of the distribution, right? It's a probability, so we can use a lot of other similarity functions to calculate the distance between two distributions, in this case, two histograms, right? For example, all right, I think I have, for example, this so-called chi-square kernel, RBF kernel, or there's another kernel called histogram intersection kernel. All of these are just basically to calculate the distance between the between two histograms. The first one is actually the L1 distance of two histograms. So here, I just show you. All right, so this is a mathematics. Sorry, the first one is not the L1 distance. Actually, it's the inner product, squared version of the inner product. So here, just to show you some examples that if the features follow some property, then it might be possible to define, some special kernel which works better than the general polynomial kernel or RBF kernel. Okay. All right. So then the observation here is, just from what we did in the case of support vector machines, right? We know that it's not possible to kernelize the linear SVM in the primal formulation. We have to somehow derive its dual formulation, such that you reformulate the original form to make the problem, the optimizing problem only depends on the inner product of the transformed features. Okay. So the two steps is we just assume. Step one was we assume this feature transform function is known, right? Then we reformulate the problem to make the original optimizing problem only depends on the inner product of the transformed features. Then we get this kernelized version. So that's how we, as long as you can basically to make the problem only depend on this inner product of the transformed features, then you are able to kernelize a linear method. All right? As long as you can do that, then you have a nonlinear version of the original linear method. Okay, so that's how you kernelize, some machine learning methods, and actually it turns out quite a few different categories of machine learning methods can be kernelized. So the key idea is to, for example, okay, so here just show you another, the first simplest example. Let's say we want to calculate the Euclidean distance in the projected space. Okay, so that's the Euclidean distance of two data points in the projected space, and it turns out we can kernelize this. Right, we do not need to know the function phi explicitly. All we need to do is just expand the original term, and it only depends on this inner product, right? So we can easily calculate this Euclidean distance as, using the kernel function. And we talked about k-means, right? So this is the backbone algorithm of k-means. Basically, you need to calculate the pairwise distance or similarity. And then based on the, the calculated neighborhood information, right? You just assign each data to its nearest center and recompute the center to update the center and iteratively run the algorithm. It will converge. So here, a key computation here is to calculate the pairwise distance, right? And when we study the k-means, we say that you can just calculate the distance using the Euclidean distance in the original space. That's what we do, right? And now we know that actually we don't have to calculate the distance in the original space. We can calculate the Euclidean distance in the projected space, right? Using this kernel trick, then we can basically kernelize this algorithm to have a nonlinear version of k-means. Okay. So then we can apply this kernel trick to k-means. Okay. So here the key is, we need to kernelize, this computation, right? MK is the mean in the feature space, in the transformed feature space. What we do is just expand this, right? We can just, if you put this MK equals sum, the mean of the data points in a transformed space, you put it back into this Euclidean calculation, and same as here, you can just make this computation only depend on the unit product of the pairwise transformed data points. Then you apply the kernel trick. Okay, the second example that we can kernelize a linear method is this kernel PCA. So this is the original PCA method. So in PCA, the first thing is we calculate the mean of the data points, right? Then we calculate the covariance matrix, because the covariance matrix, you need to subject the mean for each data point. Then you calculate the covariance matrix. And then once you get to the covariance matrix, you apply this, eigendecomposition, right, to find the largest, the leading eigenvalues and its corresponding eigenvectors. That's PCA. So if we want to kernelize the linear PCA, then we need to basically replace all of this, the original data x with transformed version, the phi x, and you calculate the covariance matrix in the transformed space, right? So we can actually calculate this kernel matrix, right? And use this this relationship to do this eigendecomposition in the transformed space. So the whole idea is that this unit product can be replaced by a kernel matrix. And here, just show you, how after you do the eigendecomposition, how you apply this the projection matrix to new data, right? Again, you also need this kernel trick. I'm not going to get into the details of this mathematics. Kernel regression is simple, actually, right? So the original linear regression is W transpose X I minus YI, and you minimize this L2 distance, right? And what you do is just replace the original data with the transformed phi I, right? And all you need to do is you just expand this, right? You expand this object function and apply the kernel trick. All right, so in order to, there's a actually this is related to the KKT condition as in the spot vector machine case, right? So this parameter, this W, this weight parameter can be represented as a linear combination of the features, right? This is guaranteed by the KKT condition. What you can do is you just partial this objective function with respect to W and set it into 0. Right? That's the KKT condition, which means at the optimal, the gradient must vanish. Right? The gradient must be 0. And if you do that, then you get this linear relationship. So you can always, represent, reformulate this W as the linear combination of the features. Right? This is the same as in the case of SVM. I asked everybody to derive the due formulation of SVM from the primal formulation. If you do that, you should see this equation very familiar. And then we put it back into the object function of the primal form, right? Then you get something like this. Okay, so now you can see that this inner product actually only depends on the this value. This is not inner product. This value only depends on the inner product of the transformed features of the transformed data, and this can be calculated using a kernel function, right? All right, I might skip some of this. So this represents the model parameters by a linear combination of the features, right? Of the transformed features. This is not a heuristic. Okay, this is guaranteed by the KKT condition. You basically calculate the gradient with respect to the model parameter and set it into 0. So this is also could represent a theorem. Okay, it's very simple. It's again, it's just one of the KKT conditions. So for the the linear discriminant analysis, which is very related to PCA. It's like a supervised version of PCA, right? We can also apply this kernel trick. It's slightly more complex than the PCA. Right? In the PCA, we have only one term. Here we have two terms, right? Which is the it's so-called within class distance and between class distance. So this is the original LDA, linear discriminant analysis. And once we replace each data point x with the the transformed version phi xi, then we get the nonlinear kernel LDA, and then all we need to do is to make the object function only depends on the inner product. Okay, so this is pretty much the same as PCA. Right? You just replace the inner product with the kernel function. Right? And well, I suggest everybody try to calculate this, to reformulate this, to make it only depend on the inner product of the transformed features. If you do that, then you will see it's very easy to find the to kernelize it. And this is also related to the last assignment, right? I believe I uploaded some. If you read the uploaded papers, you will see that actually kernel PCA, kernel ADA all have a close connection to the manifold learning. For the manifold learning, nonlinear manifold embedding methods we studied a couple of weeks ago, it's actually, the only difference is that in that case, the kernel matrix does not have a parametric formulation, okay? It's learned, actually. It's calculated using some special rules. Let's put it in that way. There's no kernel function corresponding to the kernel matrix in the case, for example, in the case of maximum variance unfolding, right? In that case, the kernel matrix is actually non-parametric. It's data-driven. It's learned from the data, okay? But in our case, in the kernel PCA, in the kernel LDA, the kernel matrix is calculated by the kernel function, right? Once you define the kernel function, give it the data, the kernel matrix is defined, okay? So that's the only difference. So be sure to read that paper, the ICML paper, which shows the connection between kernel PCA and nonlinear manifold embedding. All right, so there's a open research problem here, actually. So the choice of this hyperparameter, or sometimes it's called meta-parameters. In the case of RBF kernel, as I said, this sigma, this bandwidth, is very important, okay? It actually controls, when you calculate the distance between pairwise data points, it controls the inference of this value, this similarity, right? On the final performance of the algorithm. So this is very important. But there's no principled way to determine this hyperparameter. The best way is still using cross-validation, as we talked about, from the very beginning of this course, right? Cross-validation. So then, about 10 years ago, people developed this called multiple kernel learning. Try to learn this, or actually approximate this this kind of hyperparameters. So the idea is that okay, so let's say because I want to find a good value for this sigma, how about I don't know, right? How about I predefine some kernel functions? Let's make it sigma equals, let's say sigma equals 1, 10, 100, 1000, right? In that case, we already defined 4 different RBF kernel functions. And I assume the ideal kernel will be a linear combination of these 4 kernel functions. Of course, this assumption may not hold for real-world problem. It really depends on the predefined kernel functions. If you predefine a lot of kernel functions, then this assumption might hold for real problems, right? And then if you do that, now you convert the learning of the hyperparameter sigma into learning of the linear weight, right? In this case, the gamma, okay? So, and because this, as you can see, this gamma is, it's outside of the kernel function, right? It's a linear weight. So the problem, the learning problem, the optimizing problem becomes much easier than you learn this, optimize for the sigma. Okay, so this is the idea of so-called multiple kernel learning. But again, it's an approximation. Okay, it's not guaranteed to give you the best accuracy. But at least this is a one step forward in terms of how do you find the, a proper value for the hyperparameters. There are quite a few, papers in the literature. So if you want to know more, how can you, find the how do you optimize for the kernel parameters? You should check these papers, right? Especially the second one, simple MKL, simple multiple kernel learning. There's an off-the-shelf toolbox to implement this algorithm. If you're interested, you should have a look. All right, I guess that's the content we want to cover for how do you kernelize a method, right? It's pretty important in machine learning because for most of the real-world applications, nonlinear methods works better than linear methods, right? So, for most of the cases, we want to develop a nonlinear method. But of course, these days, for complicated problems like image classification with millions of training data, the deep learning, the convolutional neural network is a method you should use, right? Instead of using support vector machine or AdaBoost. But in any case, the support vector machine and boosting are two widely used machine learning methods, especially the data modality might be complex. For example, it can be text. In that case, maybe neural networks will be difficult to apply. All right, so that's all for this lecture. And this is the last one. So if you have any question in terms of the third assignment or in terms of examination, just ask me, and I will give you as much information as possible. Yes? Yes? Anything. No, no. Any printed material. No electronic devices. All right? So no internet connection, no phones, no laptop. Yes, that's all fine. Yes, as much as you can bring in. But I can tell you, you won't have time to check, say, books. So don't bring in any books. It's not going to help. But the lecture notes will be very helpful. Any other questions? The examination is 2 hours, okay? And it's very simple, actually. You're asked to answer maybe 6 questions. You're going to post some examples? I will. Maybe this week, but just a few example questions, not the whole, exam.
Not the whole exam, just part of the exam.
Yeah, well, not this year's, previous years, okay? All right? Yes? Both. As I said, there will be some. For example, I think I already told you multiple times, the SVM, like how do you derive the due formulation from the primal? It will be in the exam, right? It's actually in the exam every year, right? So just make sure you get familiar with this, all right?
Do we have to be able to get the primal? Do we have to formulate the primal problem?
Well, in theory, yes, right? I mean, but not in this year's exam, okay? I will give you a primal formulation, and you derive the due, okay? And also the KKT condition, things like that, all right?
Will it involve slack at all? Because I noticed there's not.
Yes.
Yeah, we'll have slack. Okay.
Yes. But don't expect I ask you to derive the standard formulation, right? It's open book. It's on the lecture notes. You don't expect that. It will be different, all right? So it's important you actually know how to, say, write the Lagrangian, right? Given a primal formulation, you write the Lagrangian, and then, from the Lagrangian function, you actually need to calculate the gradient with respect to all the primal variable and set it into 0, and you get a KKT condition, and you put it back into the Lagrangian function, and you eliminate all the primal function, only keeps the primal variables, only keeps the due variables, and then you get a due formulation, right? That's the standard procedure of how you derive a due formulation. Just do some practice. That will be in the exam. And of course, EdBoost, right? EdBoost is important. Okay. If no further questions, then that's all for this semester. And all the best.